Hello everyone and welcome to my APS talk. I am Vatsal from Physics of Fluid Group in University of Twente. Today I will try to answer the question, when does a viscous drop stop bouncing? This work has been done in collaboration with Pierre, who is a postdoc in our group, and Detlef. Before I begin, let me show you one interesting example of drop impact process. This is Scott Kelly. He is an astronaut, and in this video, he is playing ping pong at the International Space Station. For this, he's using a water drop as his ping pong ball and these hydrophobic paddles. As you can see that in absence of gravity, the spherical drop is bouncing really nicely between these two paddles. So as fluid dynamicists, we would like to model the system. So here is a schematic. Here, super amphiphobic substrate simply means that this substrate will repel both water as well as oil droplets. So this drop has a radius r naught, viscosity mu d, and density rho d, and it's falling with a velocity of u naught. Since we also want to model the surrounding, we have a surrounding density of rho s and viscosity mu s. Furthermore, the surface tension coefficient between the drop and the surrounding is gamma. With these properties and using the inertial capillary velocity and time scales, we can define some dimensionless numbers, which are the first is a Weber number, which is a ratio between the inertia of the drop and the surface tension stresses. Furthermore, we also define an Onizog number of the drop based on the drop viscosity and the surface tension forces. Further, for the surrounding, we have a surrounding Onizog number, which simply takes into account the surrounding viscosity. And there is a density ratio between the drop and the substrate, which we keep fixed for our study at 1000. So with these numbers, we have a system which is well defined. But before I should show you some numerical simulations, I should acknowledge some of my experimental friends. This paper was published earlier this year in Soft Matter from David Curry's group. Also, Aditya Jha has a presentation in this session, and I highly recommend that you watch that talk as well. Here I'm going to show a couple of videos from this study. The impact Weber number for both these cases is around 1, and the first video shows a drop impact where the Onizog number of the drop is very close to 10 to the power minus 3, which is a typical 1 millimetric water drop system. As we clearly see that that this drop bounces off without any issue. Now, if we increase the Onizog number of the drop to 0.8, then we see that the drop is unable to bounce anymore, and this impact looks like a plastic impact. Now, when Aditya and Pierre told me about this work, I was working on a similar project, which is also another example of drop impact. And this one was impact of a liquid drop on another drop. Now, what both these systems have in common is that initially the energy is stored in the kinetic energy of the impacting drop. As it impacts, the energy is transferred into the surface energy of the system, which is fed back to the kinetic energy as the drop moves away from the substrate. Of course, throughout the process, there are viscous stresses which would dissipate energy. So we thought, can we combine these two studies and use the simulation analysis framework developed for this drop-on-drop impact process and try to understand the energy dissipation in case of a viscous bouncing. And for that, we used direct numerical simulations using a free software program called Basilisk. And this program was written by Stefan Popinen. Now that brings me to the results. But before I play these two videos, let me tell you about the background color map. So on the left-hand side, we are showing the log 10 of the rate of viscous dissipation per unit time per unit volume. We are using a scale of log 10 in order to show contrast between the regions with high viscous dissipation rate and those with low viscous dissipation rate. On the right-hand side, we are simply showing the velocity vector magnitude. Now, as you can see, as the drop approaches the substrate, there are regions of high velocity between the drop and the substrate, and this is because of the air which escapes out from below the drop. Now at a low anisotropy number, as the drop impacts, there is a train of capillary wave which is formed, and all these waves focus at the top of this droplet. So let me play this video once more so that you can appreciate these phenomena. Now for high anisotropy number, we clearly see as a drop impacts, there are regions of high viscous dissipation inside the drop, and this impact process is more or less plastic in nature, and the drop never leaves the substrate. And so clearly we reproduce the outcome from the experiments. However, we would also want to understand the different forms of energy transfer in this process. And for that, we can plot energy budgets. So in this slide, I will first explain the way we calculate and plot these energies. So first, EK is the total kinetic energy of the system. So this total kinetic energy includes the center of mass kinetic energy of the drop, as well as the internal kinetic energy of the liquid, plus the kinetic energy, which is also because of the motion in air or the surrounding. Furthermore, we also calculate the gravitational potential energy. And if we add these two, we get a graph which looks like this. To this plot, we can add the surface energy and plot it as here. And this surface energy is calculating by integrating the area of this droplet. And furthermore, whatever remains, which we can also calculate, is the energy dissipation, which we can also calculate the energy dissipation inside the drop, as well as the energy dissipation outside in air. So we can divide the process into several parts. As the process begins, the kinetic energy of the drop is converted into the surface energy of the system, as you can see in this slide over here. Now, this is the location when the drop has already reached its maximum extent, and we choose the potential energy datum at this point. Now, moving on, the capillary waves which were created in the beginning of the process, now they focus at the top of this droplet, and that we can also recover by looking at the energy budget where we see some oscillations. Furthermore, the system enters a stage that we call the recovery stage, where the surface energy of the drop is converted back into the kinetic energy of the drop. If we do a similar exercise for high anisotropy number, we clearly see that the main features or the main parts of the process still remains the same. But overall, there is a high viscous dissipation as compared to the previous case. And of course, now, after this point, the drop doesn't leave the substrate, leading to a zero kinetic energy. Now we can compare the two cases together. So on the left, I will show the case with low anisotropy number. And on the right is the case with high anisotropy number. So this is the kinetic plus potential energy of the two systems. And to that, we can add the surface energy. What is remarkable in these two cases is that the location of the minimum kinetic plus potential energy still remains the same. But of course, for low anisotropy number cases, we see that the system still retains most of its energy in form of the surface energy, whereas for high anisotropy number cases, that energy is lost as viscous dissipation, which is shown in this region. Furthermore, this dotted line differentiates the dissipation which is inside the drop and the dissipation which is outside in air. So this part of the dissipation is inside the drop, whereas a small part over here at the top is inside inside air. For low anisotropy number, you don't see that difference because one, that the viscous dissipation itself is quite small, and furthermore, this viscous dissipation in air is even smaller. But we clearly see that small region coming up when the anisotropy number is higher. However, we still notice that the viscous dissipation inside air is much smaller than that in the drop. One interesting feature that people often compare is the time of contact, and it is the time which passes between this instant when the drop has just touched the substrate to the instant when the drop finally takes off, which is right about now. Now, if we look closely at this impact process, then you can see that there is an analogy between this process and the Rayleigh frequency of oscillation. This sets up a lower limit on the time of contact for these kind of cases. To know more details about this process, please read our series of papers from the David Curry's group, which really nicely explains this thing. There is another way to model drop impacts, and that is to consider the drop as a spring mass system. And of course, since these are viscous droplets, we need to attach a damper to the spring. I'm not going into details of this model because Aditya already gave a very nice description of this analogy. Now, what this spring mass system does is that it gives another prediction for the contact time, which depends on the Onizog number. In this plot, you can see that for low Onizog numbers, this contact time is more or less a constant, whereas for a finite Onizog number, this contact time diverges, which basically means that, that the drop never leaves the substrate. Now, if we plot the experimental data points on this plot, we see them that they agree very nicely in terms of the trend. And if we expand this formula for low Onizog numbers, then we can do a quadratic fit, which explains more or less all the experimental data points that we saw from the paper. Now I'm going to take away these two lines and then plot my numerical data points on top of this graph. And what we see that if the surrounding Onizog number is very small, then the numerical data points they are closer to this the spring mass analogy, and that is because similar to the numerical simulations where the Onizog number of surrounding is very small, the spring mass analogy doesn't take into account the surrounding dissipation. If we increase the surrounding Onizog number, then we see that the results are closer to the experiments, which basically means that now we have increased the dissipation in the surrounding as well. What is interesting, however, is that for low Onizog number, all these results converge to a single value, which is given by the Rayleigh oscillation frequency. And this happens because as this drop impacts and takes off, it has to undergo a full cycle of expansion. Another interesting feature is the coefficient of restitution. We can define this as a ratio of center of mass velocity of the drop immediately after the contact ends to its velocity immediately before impact. And the spring mass analogy gives a very nice prediction for this coefficient of restitution as well. And if we plot the experimental results, we see that this model explains those results quite nicely in terms of qualitative comparison. Now we can plot the results from numerics, and similar to the time of contact, we again see that for a low Onizog number, the numerical simulations are very close to the spring mass analogy, whereas they shift towards the right as the surrounding viscosity increases. Now, this can also help us to understand why there are some discrepancies between the experiments and numerics, and that could also come from increased dissipation in experiments because of the non-ideal substrate. And also because in experiments, you can have contact between the drop and the substrate, and there could be some contact line dissipations as well. Whereas in numerics, the substrate is ideal, and we assume that the drop never touches the underlying substrate, but it actually spreads on top of a thin air layer, which is always present between the drop and the substrate. What we see in both numerics as well as experiments is that there is a finite Onizog number beyond which bouncing is no longer possible. So now let us look into this bouncing to non-bouncing transition, and that we can do in a Weber and Onizog drop phase space. So initially, all the energy is stored in the kinetic energy of the droplet. And if this kinetic energy is entirely converted into the viscous dissipation during the impact process, then the drop will no longer bounce. And we can approximate these two values using these expressions. And here we can say that, okay, the deformation tensor or the velocity gradient can be approximated using the velocity of the drop and its radius, whereas the contact time can be approximated using the Rayleigh oscillation frequency. And if we use these expressions, we get that if the Onizog number is is greater than 1, then the drop will no longer bounce, which is also what we saw from experiments that very close to anisog 1, we see bouncing to a non-bouncing transition. And if we plot the numerical data points over here for high Weber numbers, we see that indeed beyond anisog 1, the drop doesn't bounce anymore, and before that, the drop bounces. Now, something interesting happens at low anisog numbers. So as you can imagine that if the impact velocity is 0, so if we gently place the droplet on a substrate, then it will not bounce. And therefore, there is also an interesting nonlinear limit which occurs at low anisog numbers, where even when the anisog number of the droplet is small, the drop no longer bounces. And with that, I come to the highlights of this talk. So we saw that viscous dissipation increases inside the droplet as the anisog number increases. We also quantified and compared the numerical simulations with experiments as well as with the spring mass analogy. And then we saw that we can characterize our results in a Weber anisog phase space. I would like to thank my collaborators, Detlef and Pierre, and I would also like to thank Aditya for sharing the data from his experiments. With that, I come to the end of my talk. Since Basilisk is a open software program, all the codes from this talk are available online at the link provided over here. And with that, thank you so much for your attention.